Okay, so I'm going to present to you guys a beam deflection problem where we have a point load instead of a uniformly distributed load across the length of the beam. So now we're going to put a point load somewhere on the beam. It doesn't really matter. It just means that we're going to impress a load at a specific point. Okay, and not across all cross sections of the beam. So what I've drawn so far is a cantilever beam. Now your bonus question will be a little bit different because your bonus question is simply supported on both sides. Okay, so the only thing that's going to change there are the boundary conditions. So you want to use your unit 3 notes on beam deflection to figure out what your boundary conditions should be. All right, but for the cantilever beam, we had boundary conditions on the embedded side of 0 deflection. It's not going to be able to move up and down. And then 0 slope here, because even if the beam is allowed to deflect after x equals 0, its slope will still be 0 at 0. Okay, so this is all going back to unit 3 at this point. Now with the free end, there's obviously going to be some deflection. The slope at that deflected end will be something other than 0. But we talked about how the curvature at that position would be 0. More importantly, the bending moment would be 0 because of the fact that you can't have equal and opposite moments on either side of an endpoint. And then by that same justification, we can say that shear force at 12 would be 0. So we've got 4 boundary conditions, 2 ends, 2 conditions at each constraint. Okay. So now what I want to do is I am going to impress a load at, let's go halfway across the beam. So we're going to go at x equals 6. Oh, this isn't really different. We're going to go at x equals 6. Okay, so halfway across the length of the beam, we're going to go ahead and impress a load of, let's say 10 newtons. But I'm only doing that at x equals 6. So I'm not impressing a load anywhere else along the length of the beam. And so what this should indicate to you is that we have an impulse function to represent our load. So our load function will not just be 10, it's going to be 10 at x equals 6. So it's an impulse because it's happening at one point along the entire thing. It's not like something I'm turning on or turning off. So we're going to use our delta function here. All right. So now what we're going to do, these are all of our little given information pieces that we're going to need. We're going to go ahead and set up our differential equation. Okay, same differential equation we started with in unit 3. It's our EI times the fourth derivative of y. And that's going to be equal to the load omega of x. Okay, and so now we have EI times the fourth derivative of y equals our load is 10 delta x minus 6. And I'm going to divide both sides by EI just to make the left-hand side nicer looking. And remember, E is Young's modulus, I is inertia. Those are going to be constants in combination, your stiffness matrix. So 10 over EI is going to be a constant coefficient on delta. Okay. So now we have the fourth derivative of y is equal to this discontinuous function on the right-hand side. So because we have the discontinuous function delta, we're going to go ahead and jump in with Laplace transforms. So I'll go ahead and say, let's take the Laplace transform of both sides of the equation. I'll apply linearity right now. So I can take out the 10 divided by EI. And then that's times the Laplace transform of delta times x minus 6. So I'm just going to make a couple of notes here. I need another color. 1 second. For the first one, this is the Laplace transform of a derivative. So I need transform 14 here, where n is 4. I'm looking at the fourth derivative of y. All right, over here, I need transform 11, where a is 6. Okay, so now we go back. Transform 14 says we'll have s to the nth power times the Laplace transform of y minus, take the degree of s down by 1, tack on the first condition y of 0. Take s down by a degree to s squared. Next condition y prime of 0. Take it down again, and then y double prime of 0. And then one more time, s to the 0th, and then y triple prime of 0. And then again, this is where we would stop because we're talking fourth order, 1, 2, 3, 4 conditions, but also we don't want to go down into negative powers of s. So there's your transform 14 with a higher order, n equals 4. The highest we've done so far has been 2. All right, on the right-hand side, we still have 10 over EI. And then Laplace transform of delta is going to be e to the negative 6s. Now, this is where it gets a little funny because we would like to be able to plug in all of the values for all of these conditions. The problem is I don't know that shear force and bending moment at 0 are 0 because I have a connection to a fixed system over here. So the only things that I can plug in at this moment are actually y of 0 is 0 and y prime of 0 is 0. But these two are still unknown. So I have to work through the problem with these in tow, and later I will be able to figure them out. Okay, so you'll be able to see that in just a moment. So let's just clean this up briefly. We have s to the 4th times the Laplace transform of y. Let me get rid of this guy. Minus. This term zeroes out, next term zeroes out. So here we are, s times y double prime of 0. And I know that y double prime of 0 is a constant. I just don't know what it is yet. Minus y triple prime of 0. I know that that is also a constant. Again, I don't know what it is yet. And that's equal to 10 over Young's modulus times inertia, e to the negative 6s. And now I remind myself that my end goal here is to find deflection y as a function of x. So I need to isolate y. Before I can do that, I need to isolate the Laplace of y. So these two terms don't have a Laplace of y attached. So I'm going to go ahead and add those to the other side. So we have s to the 4th Laplace of y equals 10 over EI times 6 e to the negative s plus sy double prime of 0 plus y triple prime of 0. And then again, I'm still supposed to be isolating L of y, so I need to divide all terms by s to the 4th. Okay, so we have Laplace of y equals, we're going to leave that 10 over Young's modulus times inertia there, e to the negative 6s. And just as before, I encourage you to write this as 1 over s to the 4th. Plus, if I take s divided by s to the 4th, that's 1 over s cubed. But hear me out. Y double prime of 0 is a constant coefficient of 1 over s cubed. So I'm going to write the y double prime of 0 first, and then the 1 over s cubed. And then in the last term, I still have the y triple prime of 0, and I have to divide by s to the 4th, so 1 over s to the 4th. Okay. So far the steps are the same as everything you've done up until now with Laplace transforms, the difference being we don't know what y double prime of 0 and y triple prime of 0 are. That's going to be something we have to figure out a little later on. Okay, so now I'm starting to think ahead. So I'm actually going to get some scrap paper out. because I have some things that are not quite what I want them to be, and I'm going to make them work. Okay. So we've talked about in the past making sure that anytime we see a power of s in our denominator or a power of t in our numerator, depending on which side of the table we're focused on, we've talked about the fact that we really want to focus in on transform 5. Okay, so transform 5, let's not forget, says if we have n minus 1 over s plus a to the nth as the form on the right-hand side of our table, then that's going to transform us back to t to the n minus 1th power e to the negative at. Okay, so I'm looking at 1 over s to the 4th. Yes, I know this is going to need 13, but I'm just trying to make sure that the pieces of 13 are going to work. I see 1 over s to the 4th here and here, but I also have 1 over s cubed. So I want to make sure that my coefficient, my numerator of n minus 1 is correct. Okay, so s to the 4th. So that means I should have s plus 0 to the 4th in my denominator for transform 5. But if n is 4, my numerator should be 4 minus 1 factorial, which is 3 factorial over s to the 4th. And 3 factorial is 3 times 2 times 1, which is 6. The problem is I don't have a 6 in my numerator here or here, so I need to put 1 in. But just a reminder that if I multiply by 6 in the numerator, I also have to multiply by 1/6 out front because I've just multiplied by 1. So that same thing will happen over here where I have y triple prime of 0 over 6 so that I can have the 6 over s to the 4th inside the parentheses. Okay, now let's work with the 1 over s cubed. So same idea. The table says I should have s plus 0 cubed down there to get s cubed. But that means that the numerator should be 3 minus 1 factorial. So the numerator is supposed to be 2 factorial over s cubed. 2 factorial is 2 times 1. So 2 over s cubed. But again, I don't have a 2 in my numerator. So I am going to divide by 2 outside so I can put the 2 in the numerator on the inside. So this is me working with transform 5 so that it is exactly what I need it to be inside those parentheses. Okay. So then once I have that done, I come back and I remember that this term here is going to need transform 13 before I can work with that 6 over s to the 4th. Okay, so I'm actually going to go through the 4 steps for transform 13 real quickly here. So transform 13, and go ahead and I identify that f of s is 6 over s to the 4th, and that the a value is this 6 up here in the exponent. Okay. And then f of t, again, using transform 5, will be t to the n minus 1, so t to the 4 minus 1, e to the negative a t, but a is 0 here because I'm not adding anything in. So f of t is just going to be t cubed, nice and simple. Then transform 13 says I need f of t minus 6. So that's going to be t minus 6 quantity cubed. And then the final step of transform 13 is to multiply that result by u of t minus 6. So we get t minus 6 quantity cubed times u of t minus 6. And so that's what's going to go in place of the e to the negative 6s times 6 over s to the 4th. But we can't forget about all this other coefficient stuff out here. We're going to need to make sure that that stays. Okay, so I'm going to go ahead and get to the next page. All right, so I have y equals, because I'm already going to take the Laplace transform, inverse Laplace transform. 10/6 reduces to 5/3. So I have 5 over 3 EI. And then the other stuff gets replaced with my transform 13 result. T minus 6 cubed times u of t minus 6. So that's just the first term. Plus the second term, I have the y double prime of 0 over 2. That's a coefficient. We're just going to leave that there. And then again, transform 5 t to the n minus 1 e to the at, negative at. Third term, y triple prime of 0 over 6. Same thing, t to the n minus 1 e to the negative at. But now a is n, or sorry, a is 4. Excuse me. N is 4 and a is 0. All right, I'm just going to tidy that up a little bit before we keep moving. So this is my deflection equation. And it's great, but it's not done because I still don't have the values of y double prime of 0 or y triple prime of 0. I still don't have these values. I just tidied up those second two terms, the second and third term. So then I start thinking to myself, well, there's got to be something I'm missing. What pieces of information do I have that might allow me to solve for these? Because these are, I'm going to consider these unknowns. And you know what, for that matter, I could consider them like C3, C4. They're constants. And at this point, they're arbitrary. So if I have two unknowns, I need two equations to solve for those two unknowns. So I'm actually going to go back to the very beginning of the problem, and I noticed that I've completely ignored the free side of my beam. I haven't even talked about that. And I noticed that there are two conditions on that free side. So those two conditions can generate two equations in these two unknowns, and I'll be able to solve. Well, in order to apply these two conditions, I need the second and third derivatives of y. So that's what I'm going to do next. I'm going to take some derivatives. All right, so this is my y. Let's go ahead and find y prime. Now, this is a little bit tricky because we're going to take the derivative of something for the very first time, and that is the derivative of u. This first term is going to require product rule, okay? So I start with the derivative of the t minus 6 to the third. So if I bring down the 3, it's going to cancel with this 3 here. And I'll have 5 over EI. And now I'll have t minus 6 squared. Okay. Plus. Now, I'm going to put a little piece of information back up here at the beginning. Something that is new to you guys. If you want to take the derivative of u of x minus a, that is delta of x minus a. But I also want to remind you that delta anywhere but at 6 is going to be 0. Because remember, I don't have any load impressed to the left of 6, and I don't have any load impressed to the right of 6. So delta at x equals 12 is 0. This function at x equals 12 is 0. And since that's where I'm going to plug in, I'm going to plug in 12. Anything with delta in it at 12 will be 0. So I am just going to say delta stuff. And I'll go through that one more time with you in just a minute. So the product rule again, derivative of the first times the second plus the first times the derivative of the second. But the derivative of u is delta, which means everything there is going to zero out. Okay. Then we have the derivative here. So this is just going to be 2t, but the 2 will cancel with the 2 in the denominator here. So you're going to have y double prime of 0 times t. I'll have 3t squared, but 3 over 6 gives me 1/2. So I'll do y triple prime over 2t squared. I need y double prime to get going here. So that's what we're going to do next. Y double prime. So we bring down another 2. And that gives us 10 over EI times t minus 6 to the first. Leave the second alone. But then the next part of product rule is going to have more delta stuff with more delta stuff. So I'm just going to combine it all and say delta stuff. The derivative of t is 1, so I'll have y double prime of 0 times 1. Bringing this 2 down will cancel with the 2 in the denominator, and I have y triple prime of 0 times t. So I can actually go ahead and plug in 12 at this point. So I'll have 0 equals 10 over EI times 12 minus 6 times u of 12 minus 6, which we'll talk about in a moment. But remember, delta at 12 is 0 because that's not where the load is. So all this delta stuff zeroes out. Y double prime of 0, and then y triple prime of 0 times 12. And then just to remind you, u of t minus 6, everything is 0 until 6, and then it jumps up and goes to 1. That's what u of t minus 6 looks like. So what is it at 12? Well, 12 is over here. So at 12, this evaluation becomes 1. Remember, u is either 0 or 1. For values less than 6, it's 0. For values greater than 6, it's 1. And 12 is greater than 6. Okay, so we can clean this up a little bit. We've got 0 equals 10 over EI times 6 plus y double prime of 0 plus 12y triple prime of 0. It still has 2 unknowns, and you know what? I don't like the 10 times 6, so I'm going to go ahead and multiply that out. So I have 60 over EI plus y double prime of 0 plus 12y triple prime of 0. So that's a little bit better, but still not helpful because I still have 2 unknowns. So then I say, well, I could use the third derivative. I'm going to give myself a little bit of space, though, to work on this. So I need the derivative of this guy up here. Okay, so y triple prime. So I have 10 over EI. Derivative of t minus 6 is 1. Leave the u. Product rule is going to bring out more delta stuff on top of delta stuff. So here we go with more delta stuff. Derivative of, where am I here? Y double prime of 0. Well, that's a constant. So that derivative is 0. And derivative of y triple prime of 0 times t is just y triple prime of 0. All right, so then if I am going to evaluate that at 12, it should give me a result of 0. So 0 equals 10 over EI, U of 12 minus 6. All the delta stuff will zero out because at 12, no load was impressed, plus y triple prime of 0. And just like before, u of t minus 6 is 0 for values less than 6, 1 for values greater than 6, 12 is greater than 6, so this is 1. So that means I've got a value for y triple prime of 0. I just subtract over 10 over EI. So if I know what y triple prime of 0 is, I can put that in up here. So I have 0 equals 60 over EI plus y double prime of 0 plus 12 times negative 10. You know what I'm going to do? 12 times negative 10 is negative 120 over EI. So I'm putting in negative 10 over EI here times 12 is negative 120. 60 over EI minus 120 over EI is negative 60 over EI. So I can add that over and I get y double prime of 0 equals positive 60 over EI. So I just got those values of y double prime and y triple prime that I was looking for. And the point is I have to go back to my final solution that I had that wasn't quite complete. It wasn't quite done yet. And I have to rewrite it with those values in there. So we're going to get another sheet of paper. I'm going to start copying this down. The first term was not a problem. 5 over 3 EI times t minus 6 cubed u of t minus 6 plus, all right, now y double prime of 0. We got that to be 60 over EI. Okay, so 60 over EI, and that's divided by 2, t squared. Y triple prime of 0, we got that to be negative 10 over EI. So negative 10 over EI, and that's over 6, t cubed. So I'm just going to tidy this up, and then I'm also going to remind you that y is not supposed to be a function of time t. It's supposed to be a function of length x. So we're just going to go in and replace all of those t's with x's. So y equals 5 over 3 EI times x minus 6 cubed, u of x minus 6 plus 60 divided by 2 is 30 over EI x squared minus, unfortunately, 10 over 6 doesn't reduce nicely, but we have that same 5/3 with EI in the denominator, x cubed. And so that is our final solution. And your bonus question will be slightly nicer because you won't necessarily need to carry through the EI. You will have different boundary conditions that you're solving for. So maybe the derivatives that you need to take are a little bit different. And that kind of thing. All right, make sure that you watch this once before you try to do the bonus. Then make sure that you're able to, keep it open and watch it, start it, pause it, rewind it, whatever you need to do. And then don't forget that you are permitted to ask questions of me if need be. But you should definitely work together on this in groups if you can. And it is due no later than 1:30 on December 7th in the final exam room.